Hello everyone and welcome to our today's talk about almost periodically stationary processes. This is a joint work of David Berger and myself. So let me at first give you the aim of this talk, then the general framework needed to understand this topic. Then we talk about the assumptions needed for the main theorem, and in the end, we also derive the central limit theorem. So the aim for today is to define a new concept of stationarity, namely almost periodically stationary processes. And furthermore, we derive conditions under which this stochastic integral is almost periodically stationary. So xt is defined as the integral over Rd of fts dls. This f is a deterministic function from Rd times Rd to R. And this L here is a Levy basis. We will talk about this later, what a Levy basis is. So this has to be almost periodically stationary, and we want to derive the conditions for this. Furthermore, we state a central limit theorem for M-dependent, almost periodically stationary processes. So let's start with the definition of almost periodic functions, which was given by Bohr. So an almost periodic function f is a continuous function such that for every epsilon, there exists an L epsilon, such that in any interval of length L epsilon, we find an tau, such that fx shifted tau minus fx is smaller epsilon for all x in R. So in the periodic case, this would be just the period, and this distance would be 0. So this was the definition given by Bohr. Now we want to define almost periodic stationary processes in a similar way. For this, we need the Prokhorov metric. So the Prokhorov metric is defined as follows. We have this collection of all probability measures, PRN, the measurable space Rn, and the probability set of Rn. So the Prokhorov metric is defined as dn mu nu. So those are two measures. The Prokhorov metric distance is defined as the infimum of all this delta greater 0, such that mu of a is smaller equal mu of a delta plus delta, and the other way around. So mu of a is smaller equal mu of a delta plus delta for all a in Rn. And this a delta is just every point in A, and then take also the ball with radius delta about this point x of A. All right. And the Prokhorov metric also metricizes the reconvergence of measures. One could also use the Wasserstein metric. This would be more general in this, for future work. All right, so now let's come to the almost periodic stationary processes. So we have a stochastic process xt, which is continuous in the Prokhorov metric, and we say that x is almost periodically stationary. Now the same definition as done in Bohr. If for every epsilon there exists an L epsilon such that in any interval of length L epsilon, we find such an tau, such that the Prokhorov metric of the joint distribution from xt1 up to xtn, and the joint distribution of xt1 plus tau, xtn plus tau, so shifted to tau, is smaller epsilon. So this is the definition we will use for almost periodic stationary processes. All right. Now we have this, and as I said before, aim is to derive conditions when a stochastic integral is almost periodically stationary. And for this, let me at first give you the definition of a Levy basis. So a Levy basis is a family LA, where A is a bounded Baryce set of valued random variables, such that L of the union of those AN is equal to the sum of LAN almost surely for pairwise disjoint sets AN. Where also not only AN has to be bounded Baryce set, also the union has to be. And LAR are independent, so I from 1 to n are independent for pairwise disjoint sets A1 up to AN. And the third condition, which reminds you on Levy processes, is there exists an A 0 in infinity, and gamma in R, and a Levy measure on R such that characteristic function is given as follows. So this is the characteristic exponent, which was stated here, and this is the Lebesgue measure of R. So A is the bounded Baryce set. This is the well-known Levy-Kinchen representation. Yeah, Here's the gamma, here's the A, here's the Labia measure. We call this triplet characteristic triplet of L, MC its characteristic exponent. All right. So now we consider now the stochastic integral. F is a measurable function. L is a Labia basis as stated before. And now our aim is before to find conditions for which this is almost periodically stationary. So the first two assumptions are that F is in L1 and L2, so Ft dot. So the second component, it's in L1 and L2 for all T and Rd. And the Labia basis satisfies this moment condition here below, the integral of R greater 1. Then R stands supremum over T and this integral, where this df is the distribution function of F, which is stated here below. This is again the Lebesgue measure of the set of all x such that ftx is greater alpha. All right, so those two conditions are needed that this integral exists, and therefore the existence of the integral. And the third condition, which is needed, that it's almost periodically stationary, will be mentioned directly in the theorem. So here is the theorem. If the above assumptions are satisfied, and if for all epsilon there exists an L epsilon and a tau in every interval of length L epsilon, such that this here gets small, so we have the supremum over the L1 and L2 norm of this difference here. So F minus F shifted with tau is smaller epsilon. And so you see the almost periodicity of this xt depends on the L1 and L2 norm. So here comes the almost periodic function assumption. Yeah. If we have this, then xt is almost periodically stationary. All right, now let's look at an example. Let's say we have a function mu, which is almost periodic in the sense of bar, which was the first definition I gave, and is away from zero, so it's strictly negative. And let L be a Labia basis with finite existing log moment, meaning this here. So finite log, or you can write it like this. Then the stochastic integral here, where this kernel function f is given like this, is almost periodically stationary. So this function here comes from as an example from Onstein-Uhlenbeck. So with mu almost periodic and away from zero, strictly negative. This would be an easy example for Onstein-Uhlenbeck. We can derive also more general cases. So yeah, this would be an example where we have almost periodically stationary xt. All right. So now let's come to our central limit theorem. So let's say we have an xt, which is m-dependent and almost periodically stationary, and also L2 uniformly integrable. Then it holds that 1 divided by square root of t, integrated from minus t to t of x dt, converges the distribution to a normal distribution with parameter 0 as expected value, and integral from minus m to m of gs ds, where this g of s is defined as the limit here, which is finite because this here inside is an almost periodic function in the sense of bar. So an almost periodic function where this limit is taken, then this limit is always finite. This also Bohr showed in his first works. All right. So what we did today was then to get a definition of almost periodically stationary processes. Then derived our main theorem, which shows that it's only dependent on the L1 and L2 norm, and also on the moment conditions on the Labia basis. And in the end, also derived the central limit theorem for m-dependent almost periodically stationary processes. Thank you very much for your attention, and see you in the meeting.